Hello all. I'm going to be going through the AS chemistry, and I'm going to be doing the May 2020 paper. And I'll be going through some of the questions, some of the answers that you should be giving, and also I'll go through some of the background knowledge as well in terms of the questions. So what I'm going to do, I'm going to take you straight to the paper, and we can just go from there. So hopefully you can see the paper on your screen. As you can see, it's the AS Chemistry May 2020 is the latest paper that's been out. I'm going to make a mark scheme for this with you, and I'm also going to give you some background knowledge. The first question, this question about atomic structure. There is a general trend in an increase in ionization energy across period 3. Give one example that deviates from the trend. Okay, so generically speaking, there's a general increase in ionization energy across the period where there's 2 dips. Generally, right, there is actually a dip between the s and the p orbital, and also the p3 and the p4. Let me tell you what I do mean about that. What I actually mean is, if you take a look at, let's just say, a period 3, for example, right? So let's just say we have a graph. We have a graph like so. So we have the ionization energy, let's just say the first ionization energy, and we have the elements across period 3. So let's just say we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. So these are the elements across period 3. So what I'm actually going to do is, when I'm actually removing the first electron, we really need to think about which subshell the electron will be removed from. So for example, if you look at, if you did write the electronic configuration of sodium, right? If you did write the electronic configuration of sodium, will be 1s2, 2s2 because it's got atomic number of 11, 2p6, so 6, 7, 8, 9, 10, 3s1. So the first electron is actually removed from a 3s1 in the case of sodium. So that's removed from 3s1, 3s2, because it's going to obviously increase in terms of the electron that's been removed as the number of electrons increase. So 3p1, 3p2, 3p3, and also notice that all 3s because it's the third shell. 3p4, 3p5, and 3p6. Okay, so like I said, there's a general increase, but there's always a dip between the p and the s. So can you see there? There's going to be a dip there. Okay, that means there's going to be a little decrease in ionization energy, and there's also going to be a decrease in ionization energy between the p3 and the p4. Okay, so that's the way to consider it. So if I just plot that for you as so I'm just going to say, for example, sodium, magnesium, aluminium, silicon, phosphorus, sulfur. Can you see the 2 dips that I'm actually putting there? So therefore it will look something like this, which is the ionization across the period. So as you can see there, there's actually a dip here, there's actually a dip there, and that's actually between the 3s2 and the 3p1, between the magnesium and the aluminium. And what you just got to say for what you just got to say to describe that, what you've got to say is you've got to basically talk about the fact there's a change in subshell. Okay, so there's a change in subshell, that means between the S and the P, okay? And also the fact that the 3p is further away than the 3s subshell, okay? So therefore, there's less attraction. So if there's less attraction, that means that less energy would actually be needed to remove that. You've also got the second dip, which is going to be here. Okay, but for this particular one, which is between the 3p3 and the 3p4, if you're going to explain that one, really consider the box notation, because in fact, right, if you actually do a 3p3 out in terms of the box notation, you can actually do this in your exam as well. You just show them that there's actually one electron in each of the orbital, whereas in the case of the 3p4, if I did that one, then technically if I did 1, 2, 3, there'll be 1, 2, 3, 4. So technically what's actually happening is inside one of the orbitals, which is there, there's actually a paired electron in the 3p4 orbital. Orbital represents one box. Orbital represents one box. So therefore, the second point you can say is they are both negatively charged. They're both negatively charged electrons. If they're both negatively charged electrons, they will repel. So if they repel, that basically means that the it's more easier to actually remove that electron away. Okay, so this is something that you are looking at in terms of the background knowledge in terms of the first question. So what I'm actually going to do now is I'm actually going to go back to the paper. Okay, I'm actually going to go back to the paper. If I go back to the paper, okay, I'll go back to this paper. So hopefully you should see the paper now again, okay, and still we are still working off that 2020 paper. Okay, so give one example of there's a general trend. Give an example, something that deviates, as I said, something that doesn't follow the general increase. So for that particular one, if I was to answer that, maybe we can say aluminium. Okay, and the reason why aluminium is one that deviates from the trend, okay, the reason why the aluminium is the one that deviates from the trend is because there is a change in subshell as the outermost electron goes from a 3s2 in magnesium to a 3p1 in aluminium. The 3p1 orbital, or you can also say subshell. You know what, I would actually go for subshell for that one. Okay, let's just say the 3p1 subshell is further away, so less attraction from the nucleus. Okay, so that's your answer there for that particular one. So give an equation including state symbols to represent the third ionization energy. So ionization energies are successive. So what that means is if you're going to give the one for the third ionization energy, you need to start with something that's already lost too. Okay, so that will be sodium, and the charge will be +2. Okay, and remember as well that you actually have to put this in the right state, so it has to be in the form of a gaseous state. Okay, sodium +2. Okay, and that's going to turn into a sodium again as a gas, but this time going to be a +3. Okay, and make sure we need to balancing it out by adding the electron on the product side. Okay, so that's your answer for that particular page. I'm going to finish off the question for you. Okay, so please just take a look at that. I'm going to carry on, and I'm actually going to go ahead and I'm going to carry on with this final question, which is the last 3-mark question before I go into something else. So it says, figure shows the successive ionization energies of period 3. Identify the element. So if you're going to identify an element just by looking at successive, right? First of all, what does the word successive mean? Okay, when they say successive ionization energy, they basically mean electrons removed one after the other. That's basically what they mean. Okay, so when the electrons are removed, okay, when the electrons are removed one after the other, okay, one after the other, that refers back to the successive. So you've got first ionization energy of sodium, second ionization energy of sodium. Actually, sodium's got an atomic number of 11, so we can have up to 11 ionization energies, one after the other. So you're removing one at a time. That's what successive means. So you've got an element X is giving you the first 10. As you can see from there, it's giving you the first 10, okay, because you've got 10 ionization energies, and you need to identify it. What I would really look for here is I'd really focus, if you're trying to identify something, I'll really focus on this part here, because this part refers to the big jump. So there's a big jump in ionization energy. Big jump, if you've got an ionization energy, means new shell. That's what that basically means. Big jump means new shell. So that means that the first 4 electrons, which are here, okay, that means the first 4 electrons which are here, okay, which are the first 4 electrons, these electrons, okay, these electrons are in the outer shell. So if these electrons are out in the shell, that means it's got 4 electrons in its outer shell. So X must have 4 electrons in its outer shell. Okay, that is because of that. So now it's in group 4 because it's got 4 electrons in its outer shell because of the big jump. Actually, wait, is that 4 electrons? Well, I can actually see one more. Let's see one more electron there. Okay, so what I'm actually going to do there is I'm actually going to extend that a bit more higher because I can actually see 5 electrons there. Okay, so if I've got 5 electrons there, then there's still the electrons in the outer shell, but there's 5 electrons in the outer shell. So that must also mean it's in group 5. So something with 10 electrons in group 5. So if you look at group 5, we got nitrogen at the top of group 5, okay, and then we've got phosphorus, okay, also as well. But nitrogen's only got 7 electrons because the atomic number's atomic number 7, whereas phosphorus it's got 15 electrons because the atomic number is 15. So technically it can't be nitrogen, but it could be phosphorus. So the element there would actually then be phosphorus, okay, it would be phosphorus, okay, and your explanation is there is a big jump between the 5th and 6th successive ionization energy, or ionization energies, should I say. This means that X has 5 electrons in its outer shell, so must be a group 5 element with a minimum of 10 electrons, which means it satisfies the phosphorus. So this is just a bit on question 1. Like I said, if you need any help with A-level chemistry or any sort of chemistry or any sort of GCSE science, if you know anyone, I'm going to put my details below. I private tutor online as well. And if you've got any questions, please just give me a shout.